corrosion model. Yes.
All right. So, does this work? You can hear me?
Hey.
All right. Great. So, thank you very much, Hermann. I will continue with the last talk on the peridynamic modeling in this mini symposium. And my talk will delve into the peridynamic corrosion model. So the fusion-driven corrosion models. You've heard Hermann briefly talk about the research aspects that we've been dealing with. And I will elaborate further on these aspects. So to give you a brief outline of what I'm going to talk about now, a historic overview of what has been done so far in peridynamic biomaterial, peridynamic corrosion modeling. And then particularly the application aspects that we've been dealing with, that would be the biodegradable magnesium-based implant materials, the design of it and the modeling of it, specifically the digital twinning aspect of it. And there are two parts to it, the electrochemical kinetics, as well as the mechanical damage analysis of a pre-corroded material. Then the continuation of this work consists in our proposed system of non-local Nernst-Planck-Poisson equations in order to capture different species and different components in our domains. And then we will go through some numerical examples in 1D, 2D, and 3D and compare them with other approaches, for example, phase field methods that have been established before that. So, the biomaterial peridynamic corrosion model was first introduced in 2015 by Professor Florin Bubaro and Chen in the University of Nebraska, and they have utilized it for the modeling of pitting corrosion in aqueous environments. This is, you can see it on the top. But nowadays, or from that point on, it was successfully applied to different aspects and to model different phenomena of corrosion. For example, intergranular corrosion, repassivation, stress corrosion cracking. Here you see mechanochemical corrosion as well, or mechanically assisted corrosion, and the research continues. Since the equations are diffusion-driven and non-local and also linearly in the kernel, they can be solved very efficiently via Fourier spectral methods, and this is a current research grant that Professor Florin Bubaro is actively promoting nowadays, so they can be solved very efficiently. What we have been dealing with at our institution, at the Helmholtz-Zentrum Hereon in Germany, in Gestach, Germany, is the application of the corrosion model, the peridynamic corrosion model, to the development and the digital twinning of biodegradable bone implant materials on the basis of magnesium alloys. So, just to give you a brief overview, you can see here the image one of those bone implant screws that Hermann has shown also before in the previous talk. The good thing about these magnesium-based implant materials is that they are naturally degrading within the human body. So they remove the necessity of a follow-up surgery to remove the implant as they dissolve naturally in the human body. They can be adjusted in terms of the corrosion. So the corrosion rate can be modified by selecting different alloys to align with the bone healing period. So when the bone is healing, the fracture is healing, the material is decreasing in its load carrying capacity, thus supporting the natural rehabilitation of the human bone. And you can see here the samples that we've been working with are rather small. Here is a little coin, and it's very difficult to see, but there is comparative size to it. There is the bone implant screw. The reason for it, is that these experimentally obtained data, they were once measured in vitro experiments as well as in vivo experiments in rats. And since you cannot put such a big bolt inside a rat, we have been dealing with rather small samples. But it can be scaled up to let's say any size, but not any size, but to larger samples as well. So it's just a representative example that we had access of experimental data to. So you've heard already from Erkan and Hermann an introduction to peridynamic equations, mostly peridynamic equations of elasticity and fracture. These models are based on, peridynamic diffusion equations or peridynamic heat equations. which are very similar in nature to the elasticity problems. So in classical local diffusion, which we also use if we are considering diffusion-driven corrosion problems, we have the concentration field variable, it's called C. This would be for us in the biomaterial approach the magnesium concentration in the field. And we have in the classical local diffusion, we have the Laplacian term. In the non-local diffusion, the idea is very similar again, that we are replacing the local derivatives, the Laplacians, with non-local operators. So we have the integral operator instead of the Laplacian operator, which takes a form similar to this. So this is one particular model that we can use with a certain cutoff radius called delta, the delta horizon. This specifies the spherical or circular region of integration. And in the biomaterial model, we consider two different phases, the metallic solid phase, so this could be an alloy, magnesium alloy, for example, as well as the surrounding liquid electrolyte phase. And we distinguish between them in terms of a threshold value. So in the sense of bonds, we can, within this delta horizon integration region, we have bonds. This is a little bit different from elasticity, so we don't have, force carrying bonds, but we have rather little pipes between two nodes, which can be considered as buckets that transfer concentration between those 2 points. So little pipes that transfer these nodal concentration fields between them. And we can distinguish different cases. So for example, if you have bonds within liquids and liquid points, we can assign different constitutive relations to it, as well as the solid liquid interface bonds from the metallic solid part into the electrolyte region. However, we usually take an assumption that we don't consider diffusion in the solid region, as this is comparatively slow if we study corrosion-induced problems. And the important parameter in this modeling would be the microdiffusivity, so the proportionality constant here in the delta integral, in the delta horizon region. So the question is how to choose this in relation to the problem at hand. And there are different approaches that have been proposed in literatures. Here is one that we have been using. For example, in the electrolyte liquid part, so the liquid to liquid bonds, we assume this is a constant microdiffusivity, which is related to the classical local diffusion coefficient. This is useful because if you think of a shrinking horizon, so vanishing non-local interactions, this should, in the limit, recover the local relations. So that's why there's also the microdiffusivity is related to the local parameter as well. In the solid to liquid bonds, we make for our problems the assumption that we define a semi-analytical volume loss. So this is something that can be related to experimental data. And based on this semi-analytical relation, we can, by means of the second Faraday's law, we can calculate the current. And thus, what we end up with is a diffusivity, which is implicitly time-dependent specifically on the volume loss of the sample. So this is a constitutive relation. There are different ones that we can use. There are different ones in the literature. But we found that for our problems, this has been working very well. And afterwards, the standard procedure of discretization of these equations, we used an implicit approach, utilizing the standard mesh-free method in peridynamics. So this summation over a background mesh with a potentially correcting factor for partially covered surfaces, and then solving these equations iteratively via the Newton-Raphson approach. You can use also explicit methods. Explicit methods are useful if the corrosion duration, for example, in pitting corrosion in salt water is rather small, within seconds or maybe minutes. Then you can use explicit formulations, but for problems like this where you have biodegradation, usually we are considering periods of weeks, maybe months. So we have been using the implicit formulation here. You've seen one of the samples in the previous presentation already. This is what we've been dealing with. This is the model of the bone implant screw, the magnesium bone implant screw. And the simulation consists in immersing this bone implant screw in the surrounding liquid environment, which is modeled as a spherical environment. And in order to enhance the computational efficiency, we utilized a multi-grid approach, meaning that in the regions where we have this this discretization of the screw, we usually need more nodes to resolve the geometry here. That's why then we combine this with the splice technique in order to have more nodes or a finer mesh or background mesh within the regions of the screw, within the frets of the screw, and the coarser discretization in the surrounding part. This is done by a implicit inverse distance weightening approach and can be directly implemented in the Newton-Raphson. The experimental data for calibrating our numerical models, the peridynamic models, were obtained by immersing the screws in a liquid environment, changing the liquid after a period of 2 to 4 days constantly, and then measuring the volume loss after a number of days. So for example, we have data up to 8 weeks of immersion, and we can then make CT scans and volume loss data in order for us to calibrate our peridynamic models based on this experimentally obtained data. So what we usually did is that we performed a particle swarm optimization algorithm in order to find the unknowns of our model. Usually this consists of the local diffusion coefficients, the kernel shape functions, as well as the saturation coefficients, saturation concentrations within the liquid environment. So what we end up with, as if you've seen before, for 2 particular alloys, magnesium alloys, we can achieve good agreement within the experimentally obtained data. One is the magnesium with 5% of gadolinium and one with 10% gadolinium. It is a rare earth metal which homogenizes very well in magnesium, and we can see that this constitutes a good match. If you want to see what this corrosion process looks like, you can see it here. You can see that this screw is continuously shrinking, and on the surface of it we have an increased damage due to the diffusion or the out diffusion of the magnesium concentration. So this is related to the peridynamic damage variable. Right. In the next step, we proposed a sequential approach in order to do the mechanical analysis, and we have already in our group established finite element methods or tools to do the mechanical analysis for these particular materials. So what we did is at the first step, we projected the damage variable from the peridynamic corrosion onto a finite element damage model, which you can see here over the course of several weeks. We see an increased damage on the surface of the frets of the bone implant screw. The peculiarity or the interesting thing is that this model, the damage plasticity model, a Rousselier model, contains a damage variable which follows an evolution equation, an ODE equation, and the initial conditions are derived from the material loss, the diffusion or out diffusion, the loss of material from the peridynamic corrosion. So if we perform the finite element analysis, we can then make predictions and projections up to several weeks and predict the load carrying capacity of these bone implant screws after several weeks of corrosion or maybe months of corrosion. And this is what we obtain. I've been saying that we've been using a finite element model. The reason behind this is that within our group we had a lot of experience using the finite element damage models, damage plasticity models for modeling this behavior, and the application of peridynamic correspondence models is not that straightforward. So we're currently also working on establishing or developing these correspondence models in order to have a unified framework. So in order to have the peridynamic corrosion, the diffusion problem, as well as the elasticity and the damage within one framework, but this is a rather challenging problem. What we've done so far is we've applied within the peridynamic elasticity damage framework, we have applied a shear load failure example, assuming a brittle material, and the results look something like this. So if you take a look here, you see that if we apply a shear load, assuming a brittle material in this peridynamic framework, we can predict the evolution of cracks. In the middle, you can see it there, the evolution of this fracture, the crack propagation within the screw. And if we take a look at the displacement, on the displacement level, we can see that the screw will eventually then break into two pieces under this shear load failure example. Right. So there are useful aspects to the utilization of peridynamic corrosion models. However, it comes with several limitations and drawbacks. One major limitation that so far most of the, or basically all of the peridynamic biomaterial models we're dealing with is that they only capture the dissolution of the solid phase in the liquid phase. So there's two phases involved, and there is only limited information on the prediction of the precipitates and their impact on the corrosion process. There have been some implicit algorithms that try to capture this behavior, but it's implicit only. So there is no real prediction of the evolution of the field variables and the formation of precipitates. Likewise, we don't have any information on the reaction terms, so chemical reactions in the system and how they influence the process, and no information on the electrostatic potential distribution. In order to model these problems, what traditionally is being done is that the n-component ionic Nernst-Planck-Poisson or Poisson-Nernst-Planck equation system is being utilized, which in 1D takes this form. It is very similar to the diffusion, the classical diffusion equation. The only difference is that we not only have the diffusion part, so the Laplacian term, we also have a part from the contribution of the movement of, well, charged particles. So if you think if we have multiple ionic particles in our liquid system, when ions move, they generate an electric field, and this electric field will then also influence the movement of, well, all the other species in our component. So charged particles have an electric field, and they influence in turn the behavior or the rate of corrosion in the end. In order to solve for the electrostatic potential, there are different approaches in the literature. In this particular system, we chose to focus on the Poisson equation with this right-hand side, the summation over all the components and the point, thus constituting electroneutrality. What we then proposed is to have this classical Nernst-Planck-Poisson system. They have this Nernst-Planck-Poisson system to transfer it into the peridynamic, the non-local framework. Just a clear, or just a little note here on the side, the terminologies are not always unique or clear. So when we say peridynamic, non-local, oftentimes we use it synonymously. But since these corrosion problems are intrinsically tied to damage, mechanical damage, we speak of peridynamic corrosion. That's why it's called peridynamic corrosion or peridynamic, non-local, Nernst-Planck system. We use these terms usually interchangeably and, well, not in a very unique and defined manner. But nonetheless, this is the non-local system that we are proposing. It takes a very similar shape as before. So we have a non-local operator of the peridynamic flux, which takes two components, one which generalizes to the Laplacian term and one that generalizes to the contribution from the electric potential. I won't go into too much detail, but basically just to give you an idea what we were doing or considering when deriving this, it is very similar to the methodology that was presented in 2012 by Professor Florian Bubaru when he derived the peridynamic heat equation. So the idea is that we are considering two infinitely long surfaces in a distance of d, so they have a finite distance between each other. We not only consider, well, two different, well, temperatures or concentrations on these surfaces, but we also consider two different potentials, a potential difference between those two surfaces. You can then show that if you shrink these two surfaces, the distance between two surfaces to zero, you would recover the classical Nernst-Planck equation. But what we do, similar to the approach that Professor Bubaru suggested, is that we keep those distances finite, and if we keep those distances finite, we get this equation, which is the non-local generalization, if you will, of the Nernst-Planck system. Afterwards, we also not going to get into too much detail, but what we did afterwards is we slightly modified the equation to have a general set of these non-local Nernst-Planck-Poisson systems. The only difference here is that we consider general influence functions, thus we can change or modify the kernels here, the integral operators, to have it slightly more general, but the structure in the end is the same. We also show that these terms, all the contributions, in the end, in the limit of vanishing non-local interactions, so as delta shrinks to 0, the integral goes to 0, this in the limit, in the leading term, recovers the contributions from the classical local equations. So it behaves as it should. It's in the limit, it should recover the classical traditional equations that we're dealing with. So let's take a look at some numerical examples. We studied problems in 1D, 2D, and 3D, and compared to similar approaches that are found in literature, specifically the phase field approach proposed in 2018. What we're dealing here is a one-dimensional wire corrosion or pencil electrode simulation. So from the left side to the right, you have a wire, and it is corroding, thus the front is moving to the left. So the wire is corroding, moving to the left. And the chemical system looks like this. We have a formation of the corrosion product, the hydroxide layer, and as well as the dissociation of water. So we have a pH value that we can calculate. When we compare this to, well, competitive, let's say, phase field models, we see that in general the structure is very, very similar, so the levels are somewhat comparable. One thing that we notice is that because we can change, or we can select the diffusivities, the micro diffusivities, based on the spatial position of a node, we can modify it. Thus we have here, if you look closely at discontinuities in these transitional layers and these corrosion interface layers, which are not captured in the phase field model so far. So this continues while we have discontinuity, or not discontinuity, but well, a kink here in the transitional layer and the interface corrosion layer. But in general, they should somehow reproduce very similar results. We then also the speed of the corrosion, so how fast does this wire move, the corrosion front, and we see that we can at least choose a set of parameters that aligns very well with experimentally available data for this, even surpassing the performance of phase field models. In 2 dimensions, keeping the electrochemical system the same, we can study the dissolution or the corrosion of a metallic plate in salt water. So what you see here, on top is the metallic phase in red, and on top you have salt water. So as the simulation progresses, you will see on the right the formation of a corrosion layer, so the hydroxide layer forming on top of the metallic phase, also moving along with the corrosion front. Down there you see the distribution of the electric potential, which makes sense. It goes to 0 in infinity and takes a finite value at the interface. And also the interesting thing is, if you take a look at the H plus distribution, we see that we have a drop in pH value at the interface, which is also something which aligns well with experimentally obtained data. Right. And last but not least, we also applied these equations to a very complex electrochemical system in order to model the behavior of biodegradable bone implant screws in simulated body fluid. So simulated body fluid has different components, different salts involved there. So it's not only, aqueous system, water or salt water, but we also have components coming from calcium or some phosphates here. So it's a little bit of a more complicated system. The electrochemical reactions at the implant surface are the same. So we have a reduction, oxidation of the magnesium phase. We have then all these equations that describe the precipitation formation based on the ions that are contained in this, well, fluid. And also we consider the dissociation of water, carbon, hydrogen carbonate, hydrogen phosphate, also in the media in this liquid part. Not to show all of the components because this would be a little bit too much, but some interesting aspects. What we see here is the solid magnesium material phase, as expected, after 2 weeks, calibrated on the speed of corrosion that we see in the experimental observable data. We see that there is on the surface a decrease, a drop in concentration, so the material diffuses out, so this is what expected. Here in the middle we have the H+ concentration, so the pH value. Also this is something that we have observed in experimentally observed data, is that we have, well, mostly a homogeneous distribution of pH, but at the surface, at the interface to the corrosion interface, to the corrosion surface, we have a drop in pH value, so concentration drops there. And the interesting thing is, for example, the electrostatic potential distribution. One thing that we have noticed, for example, that geometrically we can study with these equations is that if you take a look at the top, we have this notch, which is used in order to insert the bone implant screw. We see that, for example, in this area we have a high values of electrostatic potential. Thus, we can also model and take into consideration this geometric effects on the corrosion and distribution of the species as well as the electrostatic potential. Just a remark, usually the application of this with traditional methods, using local methods, is rather difficult because if you model the dissolution with the local equations, what you would usually have to do is to prescribe somehow the movement of this corrosion surface. Somehow you need to model this shrinking of the material. This can be combined with a moving mesh, so some arbitrarian, Lagrangian, Eulerian method. But if the dissolution becomes too much, so if the distortion is too big, then you would have to remesh, making this whole problem very complicated, especially in 3D. It becomes very challenging and not feasible anymore. So the application of these equations to three-dimensional real-world applications, industrial applications, is something very, very useful for us, and we're happy to obtain these results. I'm at the end of my talk. Thank you very much for your attention. I'm happy to answer questions.